Start. Live streaming ಆಯ್ತಾ? Okay. Good afternoon to you all, and first of all we would like to thank you for attending the Science Club program. So we have this program on the second Sunday of every month, and we have on a variety of topics, astronomy as well as non-astronomy topics, and these are more or less at a popular level, but with an effort to provide a deep insight into the subject. So the topic that we have selected for today is Kepler's laws of planetary motion, and how the three laws of planetary motion that Kepler gave almost 415 years back has resulted in a huge impact on the growth and development of astronomy. If the three planetary laws, if the three laws of planetary motion were to just describe the motion of planets known in his time, or subsequently that have been added into the solar system through our discoveries, the three laws would not have been considered as very profound ones. There are so many laws that way which specifically describe certain systems, but the profundity of any law, how deeply it impacts, depends upon how it connects up with not only the system that it originally tried to explain, but later on it has been diversified to understand how a number of systems actually work. So they all look like seemingly different systems, but they are all wonderfully unified by a handful of laws. So in that sense, the reach of planetary motion, the laws of planetary motion that Kepler gave, has been applied not just for planets, which anyway originally it was intended to, but later on it has been extended to understand the motion of celestial objects in general. And in the process, what we have found is that this law itself is inadequate in the form that it has been given. It has undergone modifications. Now, these modifications do not take away any credit from the original work of Kepler, because it has a central place in the growth and development of astronomy. So in today's session, it is almost impossible to do full justice to the complete impact that Kepler's laws of planetary motion has on astronomy in general and science, astronomy in particular and science in general. But we will try to touch upon and give you a flavor of how the laws came to be discovered. After all, you cannot take away the human aspect of science. It is one thing to mathematically describe the laws and begin from there and ask questions like where do we apply these and so on, which is more like an engineer's approach to science. The other way is to really understand what were the motivation for a person like Kepler to think about the laws of planetary motion. What were the circumstances under which the laws came to be discovered, and in the process what were the challenges that he had to undergo. These things actually humanizes the subject, which is absolutely important for any student of science. So with that intention, we will have one part of the presentation which will talk about the motivations and other questions that Kepler had and the challenges he had in his early life. And later on, we go into the actual question of the three laws that were formulated by him. And then we see what were the circumstances under which they were done. And we see that there are so many stumbling blocks that Kepler had to overcome, which are very interesting. And later on, towards the second part of the talk, or towards the end, we will be discussing about the huge impact that Kepler's laws of planetary motion have left on astronomy, and extending to not just planets of the solar system, but planets way beyond the solar system, orbiting other stars, and beyond planets, it has been applied to say comets, asteroids, and a host of other bodies, and all of them seem to follow the laws as enunciated by Kepler, originally to understand the motion of the planets of the solar system. So to completely understand the perspective in which we have to appreciate his laws, the three laws of planetary motion were arrived at by analyzing a huge amount of data that was available to him, and that's a big advantage. Okay, so nowadays we talk about big data analysis, and we look for more as job opportunities as well as research opportunities in big data analysis. It is something we have been hearing over the last 10-15 years, definitely. But the first person to do big data analysis in science definitely is Kepler, and that's one thing we see. And secondly, in the process, he had to actually invent many new ideas in order to solve the original problem. So that's another thing that we would be looking at. And then see the extension of the application of these laws way beyond planetary bodies and solar system bodies, well outside the solar system, right up to the heart of the Milky Way galaxy, as we will see. So this is the outline of the whole presentation today. And at the end of the presentation, or even during the presentation, should there be any questions, I'll be very happy to take the questions, and I'll try my best to answer the questions to your satisfaction. My satisfaction first, and then to your satisfaction. Okay, so just in case I have some things to catch up and then get back to you, my email ID is there on the screen. So kindly send your question to the email ID once again, reminding me that my answer was not satisfactory, and I will promise you to get back with proper answer. Okay, that's in the spirit of science. So let us get on with the presentation itself. So this is the first slide I would like to show you, Professor C.V. Vishweshwara, the founder director of this planetarium. And I'm not showing this slide as a hero worship or anything of that kind, but he is worthy of it anyway, of being a hero worship. He was a founder director of this planetarium, and as I mentioned on the screen, he is the bridge between me and Kepler. So after I joined planetarium in 1995, I was a raw student of science, and there were a lot of things which got polished under his guidance. And one of the things that I quickly learned from him is to realize how important biographies of scientists are if you have to really talk about the scientific work of people. You can't divorce the human aspect of doing science from the actual scientific work itself, because the two go hand in hand, and it's extremely inspirational on many occasions that you'll find that the scientific work that has been produced is not all that trivial as the books would make us believe. It is a lot more profound. So the respect for the work comes from all those things, and the person who initiated me into this way of thinking, definitely the credit is to Professor C.V. Vishweshwara. And there's one more reason why I am putting this slide here. Just 5 days from now is his death anniversary. He passed away in 2017, popularly known as the Black Hole Man of India, and there will be some relevance to his work with the Kepler's laws of planetary motion, which I will talk about a bit later on. And one of his seminal works is to give the signature of a gravitational wave, which has been used as a template in the first direct detection of gravitational waves. So the monumental work for that was done by him in 1970s, when people did not even believe in the existence of gravitational waves. Okay, now today it's a commonplace and everybody knows that it's not a big deal, but in his time it was. Okay, so for those two reasons, and there are a lot more connections which will take away all my time. So I'll stop at that point. I just wanted to remember him a few days before his anniversary. This is a good excuse. All right, so when you look at the night sky, which is the main occupation of an observational astronomer, what is it that you see? You see dots of light against the background of a pitch dark sky, if you are fortunate. But if you are a Bangalorean, then even that is taken away from you. Pitch dark sky is next to impossible, and seeing a few dots, you should be very lucky if it is not cloudy. So this is what you see, and looking at these dots of light in the night sky with your unaided eye, all that you can observe is color and the brightness. But to know that a good deal of astronomy progressed during this particular phase when people practiced astronomy with unaided eye until the invention of telescope in 1609. So a lot of progress has been done even with the unaided eye observations. So immediately we see that by looking at these dots of light from one night to another night, and if you are observing over a long period of time, of several years, then you try to make certain patterns about these dots of light that appear, because they are not always in the same position in the sky. They keep changing their positions, and if they changed positions randomly, there would be no science. There would be no science as a subject, I'm telling. And if they did not move at all, if they did not change at all, again there would be no science at all. The important thing is that they move, and they move in a certain pattern, and that makes it something affordable for us, reachable to the human beings, reachable to our way of thinking, and we try to find pattern in the motion. And one such thing has led to the Kepler's laws of planetary motion. So this is all we can see. And so what were astronomers studying with light received from stars and planets? I just now mentioned to you that it is possible for you to observe the changes in their positions, and these changes would help you to understand how they actually move in the sky. And one of the important things is that, interesting things is that the stars are so far away from us that from 1 year to the next year, you would not see any appreciable change in the position of the star in the sky. So they behave like a graph sheet on the screen, on the sky, and you can plot all the points on the graph sheet. And if at all there is any object which moves in the sky over a period of a few weeks or few months or a couple of years, then you will be able to actually mark the positions with the fixed stars in the background as a reference. So that is a very important, interesting thing. It looks like nature has made these things just in a way that we can comprehend the motion of objects. Okay, so you mark positions and so on. Now it is not such a trivial practice. It's not a very trivial exercise that night after night you watch and then you put all the dots on a graph sheet and you mark the positions. Now that is not a very trivial exercise. So it actually led to, I know that I'm jumping, I'm actually taking a big leap now from that to arrive at this particular point. You will actually be able to find out how these planets actually move in the sky. Okay, planets have a relative motion which is easily observable over a period of a few weeks or months against the backdrop of fixed stars. As a result, the motion of planets can be easily discerned over several years. And that's exactly what people did. And what did they arrive at? They arrived at the fact that Earth is the center around which everything else goes. Now, nothing can be more natural to the unaided eye, or even if you were to look through a telescope, that everything rises in the east and sets in the west, and they all seem to be going around. So, geocentric model is a very natural model if you want it. All the objects in the sky appear to go around the sun, around the Earth. Now, to say that this is not the reality, but the reality is something else, is not very easy. But still, the human mind has achieved that. That's a very interesting thing. So for 14 centuries, people believed in this, and in order to understand how planets actually moved around the Earth, after all, they observed patterns over several months and years, and to fit those patterns in a predictable way, suppose I want to know where Mars is going to be observed in the sky at 2 a.m. In 2028, March 25th. I should know what pattern of motion Mars follows. Then I simply have to use that pattern to predict where it is going to be. Not only that, if the pattern is true, pattern will always be true. It is our understanding of the pattern which could be right or wrong. Okay. So, well, in the past, you can also find out where Mars was on a particular day, a particular night, at a particular time, as seen from a particular place on the Earth. So you can go back in time and predict the positions of, I don't know, predict if it is the right word. You can extrapolate the position of the planet as it was some years back, or you can even predict where it is going to be some time in future. So this predictability power comes if you are able to exactly fix the pattern that it follows. So any law in science precisely gives you that power of getting the pattern. So in order to understand how these planetary positions could be predicted, people came up with a very complicated model. And in this complicated model, so there would be the Earth and there would be planets going around a particular circle around the Earth, and the planet itself is not here on the circumference, it would be going on the smaller circle, okay, called the epicycles. Now, what should be the size of this bigger circle, what should be the size of the smaller circle, and sometimes there is a line joining the circumference of the big circle with the center, and sometimes it joins a point which is a little off center. How much of off center it should be? These things really made it very, very complicated. But still, that was the best thing that people came up with in those days. And with this complicated explanation, they could still find patterns in predicting the positions of planets. And to cut the long story short, once again, then Nicholas Copernicus came, and then he showed that Earth is not the center of the universe, it is the sun which is the center of the universe. In those days, universe meant solar system. So our concept of universe itself has expanded with time. So that is why you will hear words like geocentric model of the universe and see heliocentric model of the universe. By universe, you will see only picture of the planets going around the sun. So that was the universe. So you had this. Now, one interesting thing that Copernicus did is that he not merely told that sun is the center around which all planets go, including the Earth, but he proposed this as a model. He didn't claim that it is a fact. There are reasons for that, why he did not claim it as a fact. Let's not get into that. But he proposed it as a mathematical model, as a mental model, as one possibility that planets could be going around the sun in this fashion. And in the process, one great improvement that he made over the previous model, where Earth is the center of the universe, Earth is the center of the solar system, is that the order in which the planets had to be in terms of distance from the sun, that was fixed. Of course, you should ignore these two. Copernicus did not know about Uranus and Neptune. He knew only about these planets up to Saturn. So he knew exactly where the planets should be. So Saturn could not be put in the place where you have Mars. Mars could not be placed in the place where Mercury is. But in the previous model, the geocentric model, you could do that. If you just adjusted the radius of the two circles, it was possible to put any planet at any distance from the sun, from the Earth, and it could still explain the periodicity of the planets that you saw in the sky. That's the beauty of that. But in Copernicus's model, that was not the case. He told it had to be in the order of Mercury, Venus, Earth, and so on. And he also measured the distances to these planets that were known in his time in terms of Earth-Sun distance. Okay, the Earth-Sun distance is called astronomical unit, and in terms of astronomical unit, he gave the distances to all other planets. So this is the first step towards Kepler's laws of planetary motion. If you just thought that I have forgotten Kepler for some time, this is the first step. And then comes Kepler. People were happy with the description of these positions, but Kepler was a man of was an astronomer of a slightly different kind. He was obsessed with the geometry. He believed, I mean, all philosophers believe in certain ideologies. They think nature works in a particular way, and that is their universe. So every philosopher had their own universe. Kepler also had a universe because he was also a deeply thinking person, namely philosopher. So he asked an interesting question, which he says in his book as the greatest thought of his life. This was the greatest thought of his life that came to him, and at that time he was actually teaching in a classroom, and was teaching some theorem in geometry, something that is taught in classes 7 and 8 nowadays. And the problem was to find how to draw a circle inside a triangle such that all the three sides of the triangle just about touch the circle. So this is called incircle. Then to the same triangle draw another circle, bigger one, which will just about touch the three vertices of the triangle. So this is called circumscribing a triangle. So you have to circumscribe and inscribe to a given triangle. That was a problem he was trying to solve. And while solving this problem, particular problem, he was bugged with a very interesting question which came to him very often, and it is said that even in his dream he would actually try to answer questions to this. Kepler was a very peculiar kind of a person. The question that bothered him was why there are only 5 planets known to us. 5 planets known to us in his time. So Mercury, Venus, Earth, Mars, Jupiter, Saturn, 6 planets. Sorry, not 5, 6 planets. Why there are only 6 planets? So he wanted to find a mathematical answer to this question. And that was when he was solving this particular problem. So when he was trying to solve this particular problem, it is said that Kepler, he had a habit of suddenly breaking up from the class that he was teaching, go to the corner of the board and start scribbling something and keep mumbling to himself. The whole class would not know what Kepler was doing, but Kepler would be completely working on a different problem, not the problem that he was teaching in the class. That was his habit. So he went into one such ecstatic moment when he was trying to solve that problem I showed in the previous slide, and suddenly he realized why there are only 6 planets in the solar system. Now this is a very curious way of doing science. You're talking about planets, you're thinking about planets, and you're working on a problem in high school geometry, and suddenly you find that geometry is able to give an answer to a very philosophical question like why there are only 6 planets. I mean, that was how people sometimes are inspired by. So when he realized it, his excitement knew no bounds, and in his own words he said, so these are the ways he tried to fit different objects one into the other. This was a mathematical problem that he was trying to solve, how different polygons can be inscribed and circumscribed, and suddenly he found that, oh, there are 6 planets and there are only 5 Platonic solids. Okay, I'll show you what those Platonic solids are. These are the Platonic solids that is. There are 5 Platonic solids. There is a theorem in geometry which tells you why there can be only 5 Platonic solids and not more, not less. Okay, this comes from some arguments from symmetry. And one hallmark of these Platonic solids is that they are made up of regular figures. So either you have regular pentagons, regular quadrilaterals, which is a square, or a regular triangle, which is an equilateral triangle. So using these, there are only 5 objects that you can do, 3-dimensional objects. So he felt that this is a nice way to do. This is Kepler's universe, Kepler's model of the universe. It's a geometrical model of universe. Kepler was obsessed with geometry, I told you. So you have nested spheres in which you have different Platonic solids, and the spaces between these 2 Platonic solids would be the orbit of one planet. So if you have 6 planets, you can fit orbits into 5 spaces given by 5 objects, 5 Platonic solids. So that was a remarkable realization for Kepler, and it seemed to be a very logical deduction that only 6 planets are possible because there are only 5 Platonic solids. Now to you and me it looks very funny, and we may even say that it's a very stupid thing of Kepler to think that number of Platonic solids decides how many planets are going to be in the solar system. But to him it made perfect logical statement, because he felt that the whole universe is governed by principles of geometry, and the principle of geometry tells there can be no more than 5 Platonic solids. There are only 6 planets that you see, and everything is fitting into place, literally and figuratively. Okay, so that's what he did. And then with this kind of an intuition of connecting the problem in geometry with something in astronomy, it would come only to a prepared mind. It doesn't happen to everybody. Because he was continuously working on this problem, why there are 6 planets, why there are 6 planets all the time, his mind was continuously searching for an answer to this question, and the first instance when he thought that it answered, he was really excited. Okay, there are a number of instances in science where you may say that oh, this happened by chance, or he should be lucky to have done this. Luck doesn't bring anything to anybody. Luck can actually make you see something, but if you want to make sense out of that, you should have intelligence. To see that what you are seeing is very profound, you need intelligence. So without that, you cannot make serendipitous discoveries or chance discoveries or accidental discoveries. So this accidental idea that that Kepler got, it was because his mind was prepared. Okay, this is what happens to us also. You know, whether we are teaching, we are doing research, or we are doing some household work, only if there is a prepared mind with the problem that is burning all the time, you will see a solution even when there is no connection between that and the problem. Okay, but in order to do this, the Copernican model was very, very important, because in the Copernican model, you know, you actually found he gave the distances between a planet and the sun. And what Kepler found was the following. Kepler found that the distance between Jupiter and Saturn is exactly, not exactly, very nearly a factor of 2. Okay, and then when he tried to find the ratio of the diameters of the orbits of Jupiter and Saturn through his model of Platonic solids, he exactly got the ratio to be 2. And he found that it could not be anything more than divine providence, that God created these planets at specific distances from the sun, and he also gave us these Platonic solids, and the 2 characteristics actually matched. So it was not a very convincing thing to Kepler to believe as to why Platonic solids, number of Platonic solids decided the number of planets. Now what has this to do with planetary motion, laws of planetary motion? We will very quickly come to that. Okay, so this is in his own words, the things that I explain to you in a common man's language, has been poetically put by Kepler there, what it is. And but today we know that there are more than 6 planets. Okay, we have become the masters of deciding about the number of planets. You define planet in a certain way, you can have 9 planets including Pluto. You define planet in some other way, you can exclude Pluto and you have 8. Or you can come up with another definition with which you will have 15 planets in the solar system. And definition is man-made, human-made. So definitions by themselves are not logical, but they are for our convenience. They help us in many ways, so they are not completely useless, but you should not try to look at too much of science into the way it is defined. So the question of if Kepler had been alive today and seen that there are so many planets, I don't know what kind of geometrical reason he would have come up with to understand why there are 8 planets in the solar system. It's a thought we can harbor. Then we make quick strides into the path leading to the 3 laws of planetary motion. Now Kepler was so excited about his model of the universe, which we saw a little while before, that you have all the planets one nested into the other using 5 Platonic solids. He published it as a book, okay, Cosmographicum Mysterium, which means the cosmic mystery. So it was a mystery to him why there are 6 planets, and he is the only person in the universe to explain why there are 6 planets at that point of time. And needless to say, he wanted to publish it to the whole world, and he published it as a book. And this book was read by, in particular, Tycho Brahe, this person, and Galileo. Out of many names, I am taking these 2 because they are the 2 important names for our story today. So it was good that they came to know, and Kepler had a long and a very happy association with Galileo after Galileo's telescopic works especially. Galileo had only Kepler to appreciate what Galileo had found out through the telescopes, because there are many, no other, either from the common public or from other strata of the society who went with Galileo's ideas. So the only person who really appreciated Galileo's work was Kepler, so they had a long friendship. And Tycho Brahe was a mentor of Kepler. So after having seen this, Tycho writes to Kepler, very impressed by Kepler's work, "Come not as a stranger but as a friend, come and share in my observations with such instruments as I have with me." Now by this time, Tycho Brahe has made a huge observatory, because the instruments of measurements were very huge. What were the instruments he made? He made huge protractors. Nothing more than that, huge protractors which could be of the size of this room. Now, what is the difference between a small protractor and a big protractor? 1 degree on a small protractor is still the same as 1 degree on a large protractor. Okay? But what it does is, on a small protractor in 1 degree, if I ask you to make 100 divisions so that you can measure 1/100th of a degree, that's not easy. But if I have a large diameter protractor, again 1 degree space will be the same, but now you have more space in that 1 degree and you can make 100 divisions. Least count will be reduced. Fantastic. That's the right way to put it. Least count will be reduced. That's exactly what Tycho Brahe had in. He realized that big instruments are very, very essential. And why did he make this big instrument? Just a few minutes back I told you that all philosophers had their own universe, their own models of the universe. Tycho also had a model of the universe, which was a combination of what Copernicus gave and what people before him like Ptolemy had given. It was neither geocentric nor heliocentric, but a combination of the two. So in his model, Tycho Brahe's model, which is also reflected in the Kerala astronomer Nilakanta Somayaji's work, independently, Nilakanta Somayaji also came up with a similar model where all the planets go around the sun and all these planets go around the earth. So it's a happy marriage of two systems. So Tycho wanted to show that this is correct. But where Tycho Brahe is different from astronomers before him is that he did not simply give it as a model and say, follow this. Or he did not give a few reasons as to why this model should be correct. What Tycho Brahe did was, if I have to convince people about my model, I have to do it through measurements. Entire branch of science rests on measurement. No measurements, there is no science. Okay? So he wanted to make measurements and use that to convince people. And to make precise measurements, he needed precise instruments. And to make precise instruments, he must have had very low least count, and for that he had to make very huge protractors to measure the positions, angles, and so on. Like I told in the very first 1 or 2 slides, that all that you can measure is the position, but it's not a trivial one, I said. And why it is not trivial, we realize completely now. Tycho Brahe took something like 20 long years of documentation of positions of these planets. On every single night the skies were clear, he would go and do it. So much of data had been collected over 20 years. But he had a problem. The problem that he had was, he wanted to understand the shape of the orbit of Mars. And in his days, philosophically it was believed that all orbits have to be circular. Okay, because after all, God has made this world and God has to be symmetric from all sides, because if one side is more than the other, there are other kinds of problems. So it has to be completely symmetrical, and the most symmetrical one is circle, and therefore circular motion would be the most perfect motion. Therefore the orbits were circular. Okay, and Tycho Brahe's measurements actually show, measurements of the position of Mars over 20 years of time showed that it was not a circular orbit. So he was bothered. Should he dump the philosophy of his predecessors and say that it is not circular? In which case he has explained what else it is. If it is not circular, what else it is? He didn't have an answer to the second question. If not circular, what it is? So he spent a long time on this. And when he read Kepler's the Cosmic Mystery book, he was convinced about the mathematical abilities of Kepler so much that if there is one fellow who can actually crack this problem of the shape of the orbit of Mars, then it has to be Kepler. So he got, that is why he sent this wonderful invitation. And it was not very smooth sailing, because all the data was not given to Kepler by Tycho Brahe at once. This is the hallmark of a good teacher. You don't say everything to your student. So you keep a few things, a few tricks in your bag, so that he or she keeps coming to you time and again. And that is what Tycho Brahe did. He wanted Kepler to be interested in him, in his work. So he would give a little bit of data today and a little bit of data a few months from now, and then give small problems and so on, and test if Kepler was interested. But Kepler, being a very good student of science, he knew what was in Tycho Brahe's bag. So he took all these small cookies only because he wanted the big meal later on, access to the entire data. And unfortunately, before Tycho Brahe could solve the problem, he passed away. But what good thing he did was to bequeath all the data that he had collected to Kepler. He said, none other than Kepler will have access to the data that I have collected. That's the best contribution of Tycho Brahe to astronomy. Because right kind of things falling into the right hands at the right time is the right thing to happen. But we never know what is the right sequence. But it happened in the case of Kepler. So Kepler looked at the data that he had, 20 long years of data, huge amount. So anybody can actually find a pattern in the way the Mars planet goes around the sun. He said that I am going to solve this problem in 8 days. That was a very boisterous claim that Kepler made. In 8 days he would do it. But history tells us that he took 8 long years to solve that problem. Okay? Great Kepler took 8 long years. And in this period, Kepler had to do quite a bit of geometrical theorems, prove for himself, and use that data to solve the problem. But the interesting thing is, I think I have it somewhere here. Yeah. The interesting thing is that there is a difference of just 8 minutes of arc. This is a unit of angle. About 1/4 of the angular size of the moon. The moon that you see in the sky has an angular size of half a degree or 30 minutes. By angular size, what you mean is you take 2 rays of light from your eye, connect to the 2 diametrically opposite points on the moon, measure the angle between these 2 rays, you get roughly 30 minutes of arc or half a degree. Now, if you actually fitted the orbit of Mars, it was nearly circle but not exactly circular. How much of a deviation was there from being a circle? Just by about 8 minutes of arc. Okay, which is roughly about 1 minute of arc is about 1/3600th of a degree. You can imagine how small it is. Interesting thing is, it's just 8 minutes difference. Now Kepler had two options. One, say that Tycho Brahe actually made an error of 8 minutes of arc. Actually the orbit of Mars is circular. Declare that. Because out of so many points that he had in 20 years of data, in that one orbit, Mars does not take 20 years, but in one orbit, only 2 points did not fit on the circle. All the points that he measured exactly fitted on the circle, but only 2 points were misbehaving. Now you could say that it is just an instrument error. But Kepler knew how precisely the instruments of Tycho worked. This is very important for a researcher. If you want to make any comment on the measurements that you have made, you must know how precise your instrument is. What are the errors in the measurement of this instrument? Either because of the measurement method that you are having, or because of the construction of the instrument itself is having some inherent error in that. You have to know that. Kepler knew this exactly, and he said, Tycho's measurements cannot be in error for more than 2 arc minutes. Therefore, 8 minutes of arc is too much, 4 times more than what? And he had so much faith in the precision with which Tycho could measure that he said, my guru could not have gone wrong by so much. So he went on toiling for this, and that's the reason why it took him 8 long years. What did he do in this during this particular period? Okay, this is just to give you an impression of how Tycho's observatory was. And there are other stories. I'm running out of time, so no time for stories. The important shift in Kepler's way of thinking is that in most cases before him and also during his time, people would come up with an idea about anything and then make measurements to fit that idea. That was a standard procedure. But Kepler was exactly the opposite. He went with a clean mind. He did not have any particular hypothesis that the circular orbit, that the orbit has to be circular. He said, whatever the data is there, I should fit my data to that particular, I should fit the curve to that particular data. Exactly. So that's a very big shift in the way you think. Okay. So he wanted to get the shape of the orbit. But the important thing is, he comes to a very important realization. In 20 long years that Tycho Brahe has made observations, Earth is not still. Today it's a very obvious point to us that Earth is not still and it goes around the sun. But in Kepler's time, when people believed in geocentric model, Earth had to be still. Now, if you want to crack this problem, the first big stumbling block that you have mentally is to give up geocentric model and say that I believe in heliocentric model. Kepler did that, fortunately for us. The moment he went into heliocentric model, he had liberated Earth from its center, fixed, non-moving, immobile, static position, and he let it free to go around the sun. And in the process, he got into a bigger problem. What is a bigger problem? In 20 years, all the positions that Tycho Brahe has measured, it is from a moving platform. Earth is going around the sun. So when you measure Mars today, Earth is at some point with respect to Sun, Earth and Mars. 3 months from now, if Tycho Brahe has measured the position of Mars, it's not from the same position, but it has moved to some other position. Therefore, if you want to exactly fix the position of Mars, as seen from the Earth, you have to understand how Earth is going around the sun. So first you have to believe that the Earth goes around the sun, which itself is not easy. Do you see the problems that Kepler has? It's not just formulating the planetary motions, but there are a lot more mental problems that you come up with because of the way we have been taught. So like all of us, Kepler was also taught by his teachers, and it was geocentric model. So he had to disband that. So he comes to this realization. So this is no small realization. But once you realize that this is the way to go about solving a problem, half the problem is solved. So what did he do? This is a little bit of a tricky slide. I'll just explain to you very quickly. So suppose you start marking the position of planet Mars today. Let us say that the sun is there, the Earth is here, and Mars is there. Now you find, as seen from the Earth, this is the direction in which Mars is. Now after some time, the Earth would have come to this point. Now the direction of Mars as seen from this Earth would be in the direction of some other star. It would not be in the direction of this particular star which you started with. Now you keep doing this for the entire set of data that Tycho has measured for Mars. You actually find that Earth has actually gone around the sun once in a particular period, in 1 year as we call, but the Mars has not completed one revolution yet. So for this particular orientation to be repeated, it takes about 2.2 years. Because Mars has to complete one revolution around the sun, it takes about 2.2 years, and that's what he realized. But the problem that he came up with was the shape of the Earth's orbit that he deciphered from this exercise was also not circular. So in the process of looking at the orbit of Mars, which is not circular and already had one problem, now he had to explain why two planets don't have a circular orbit, which is double the problem. But one interesting thing that happened there was, in the process of this, he found out that, I must mention this, if you have to do this, you should know on what date where the Earth is, for which you have to be a very meticulous observer. So Tycho Brahe's record was so meticulous that he would actually put down the date and time of observation very precisely. So time measurement is of absolute importance in astronomy, in entire science, more so in astronomy of this kind. Tycho had done that. If Tycho had only made a record of positions, but he had not been very careful to record the date and time, Kepler could not have done this problem at all, in spite of having the data, because you don't know on what day where the Earth was. But now he had, fortunately, and then he constructed the orbit of Earth, and in the process what he found was in the months of around January, Earth covered a greater part of the orbit. It covered a greater distance on the orbit, and in July, it covered a smaller part of the orbit. It's as though the speed of Earth had changed in a matter of 6 months. Now, if you do this for every year, then you find that every year during January you have the same problem. Earth is moving faster, during July it is moving slower. It is one thing to observe, it is another thing to interpret this. To understand what this means is not a small thing. So he came up with what we call the second law of planetary motion, and that was the first one to be discovered by him. Okay, and this is the law. If you take a line joining the sun and the planet Earth, and then you let it sweep around its orbit like this, and between two instants of time you get something like a small triangle, okay, almost a triangle. If you find the area of this triangle for different intervals of time all through this orbit, you will find that the area covered by the triangle is the same. Whether the triangle is big, slender and tall, or thick and short, the area of the two triangles would be the same. This is called the law of areas. This was the first one to be discovered by him. So this came as a bonus. He was trying to find the orbit of Mars, but then he found out something else. And then to actually find out the orbit of Mars, it took him much longer time. He knew that if it was not circular, it looked like some kind of an oval. Oval we use in our daily life language in a very loose sense. Anything which is egg-shaped is also oval. Egg-shape is one kind of oval. There are many kinds of ovals which are mathematically described. So what kind of an oval is that? Ellipse is one such oval, if you would like to call that. So he realized that it is an ellipse, and this was after trying to fit the orbit of Mars to 70 different kinds of curves known at that time. So there were so many curves which look like oval, so he would take the data, put into that, find out. It runs into several hundreds of pages of Kepler's notebook, where he tries to fit the shape of the orbit of Mars with known shapes in geometry. After 70 trials, he comes up with this. Now you may say he was very lucky to be doing this for the 71st time. Again, remember, you should be a prepared mind if you have to accept that. So the law of ellipse, which is the first law of Kepler's law of planetary motion, was discovered second actually. So when he fitted this ellipse into the Mars's orbit, bang on, the two misbehaving points also started behaving in an orderly fashion, and they were put on this ellipse. And exactly the same thing with Earth. So Earth had an elliptical orbit, Mars had an elliptical orbit. So he had no hesitation in arriving at a general rule that all planetary orbits around the sun is elliptical. And he was fortunate to do that because it so happens that the orbits of other planets also follow the same elliptical path. Okay, so the two laws. Now, he publishes this, and those days it was fanciful to publish everything in Latin. Okay, that shows that you are a very intellectual person. So if you did it in your local language, Kannada, then you are not very intelligent. So you had to do it in Latin. So he does this. This book is called New Astronomy, Astronomia Nova. So what is this new astronomy? This new astronomy is people were doing astronomy in the sense of marking positions only, and now the new astronomy gives you a handle to predict mathematically about the orbits of planets and also the speeds at which the planets go around the sun. So it became a regulated mathematical universe, geometrical universe. It was not static, it was a dynamic universe. Okay, sorry. So this was in the 17th century, like I told you, Galileo's time. Does he mention the year there anywhere? It should be. Madam, nimge ಏನಾದರೂ ಗೊತ್ತಾ? So that's around the 16th century, 17th century. Then we can ask this question because there are a good number of students here and also watching online. Hopefully, I thought I'll include this. This is a very good question to often ask, what if? So now you can see that what if Tycho had if Kepler had not published this cosmic mystery? What if Tycho had not read and appreciated it? What if Tycho had not invited Kepler to join? What if Kepler did not join? Then what if Tycho's instruments were not very precise? What if Kepler doubted 8 minutes of arc as an error by Tycho and not a real thing? So you can go on asking this. Now you see that the process of arriving at these two laws we have seen so far, there are too many coincidences that we cannot actually logically answer. So many things that happen. It looked like a perfect mix of random things and order comes out of that. Okay, so that is the point that we try to appreciate. So this is a thing that you do with everything that you learn about, whether it's history or science or history of science. What if? It's a good question to ask. Okay, I'll skip some of these quotations. I'm tempted. Okay, you can just read up for yourself. It's on the screen. So it took 17 long years by now, by the time two laws came to be discovered. Remember, he promised to solve the problem in 8 days, but it has taken him 17 long years. So even a genius like Kepler needed that kind of time. But after all, he was doing big data analysis without any computational instrument, no computers. But he had to do 20 years of data, which is not a mean thing. Dr. Sita from ISRO is here, who works with such data from satellite missions, and she can vouch for how difficult it is to have these data analyzed manually. But Kepler had to do it. There was no other way. That's why it took long year. So now if people like Dr. Sita can do it in about 5-6 months of data, it is thanks to a very important procedure that Kepler invented. I have not come to that point, and which he introduced, because of which big data analysis has become much easier. So what you can do in 17 years now, you can do in 6 months. So not surprisingly, people in Kepler's time told that Kepler, by introducing this particular concept, which I'll come to in a short time, he had doubled the lifespan of astronomers. That was what was told. Because whatever time they spent on calculations, now they could look up at the sky and get more data and maybe look at more finer patterns there. Okay. So Kepler's third law, which is related to how planetary distance and the period of revolution depends, was actually inspired by his interest in music. Somehow he felt that everything that happens in the universe happens in a harmonious way, and he wanted to seek this harmony in the universe. And somebody who was very much deeply interested in music, he was trying to look for an answer through that. Inspiration can come from anything. Okay, finally, if you look at the factor that inspired him and the concept that, or the idea that he arrived at, the two are not connected. That doesn't matter to us as long as we get into the right direction. Okay, so he wanted to do this, and which one? I was running out of time, so I thought I'll skip that. You have a very sharp eye. In fact, this is what he thought. He actually translated the orbital motion. Let's not spend time on that. What it tells you is that Kepler looked at the motion in a very musical fashion, and then he created even musical notes to represent the motion of these. So Mercury has a certain kind of a very pacey music, because Mercury goes around the sun very quickly in about 88 days, and Saturn and Jupiter have much longer time, so the music is more relaxed and a slow moving music. And this is the new notes. And actually it was Professor C.V. Vishweshwara who got this music to be composed based on this from a music director. When we made a program on Galileo, there was a music director by name Mr. Ravindranath Shenoy, who is no more, but an extremely creative one. So we gave him these notes, musical notes, and he was asked to compose, and that's what I was going to play. Okay, maybe at the end of the talk. So he found out that if you plot a graph of the time taken by a planet to go around the Earth, to go around the Sun in once, and against the distance of the planet from the Sun, you'll get a graph which is curved like this. All scientists would like to plot graphs in such a way that you get a straight line. Okay, this has to be a straight line. If this is a straight line, then you can immediately say that whatever you have plotted on the y-axis is proportional to what you have plotted on the x-axis. Everybody wants that. But then nature doesn't care for our difficulty. It says this is the pattern that is followed. Now you figure out how should you plot the graph now so that you get a straight line. In Kepler's time, this was mathematically a tool. It was not a tool that was available in mathematics. So Kepler had to invent something which is nowadays unfortunately not taught seriously at high school. Once upon a time it used to be. This is related to a concept of logarithms. Okay. Now to put in a very simple way, logarithms works like this. If you take a normal scale, the distance between 1 centimeter and 2 centimeter is the same. Between 2 centimeter and 3 centimeter is the same as between 1 and 2. This kind of a scale is called a linear scale. Okay. In logarithm, what you do is you take the ratios. The distance between 1 and 10 is same as the distance between 10 and 100. The distance between 100 and 1000 is the same. But the ratio of 10 is to 1 is same as 100 is to 10, is same as 1000 is to 100, and you plot the curve. This is called logarithms. But not as simple as I have mentioned. Kepler took a few years to invent logarithms and also invent many of the theorems related to logarithms. Because some students are there, I'll just mention. You say log of m into n is equal to log m plus log n. Log of m to the power of n is n log m. These theorems were actually derived by Kepler, and he had to be sure that they work. And then he used the result of all these things to plot the graph in a different way. So now the thing is, you have a logarithmic scale. This still looks, this is a wrong scale. But what you are plotting is t squared versus a cubed. T is the time taken for the planet to go around the sun once, and a is the distance of the planet from the sun. If you square one and cube the other and you plot, you get a straight line. But this is because we know the answer today. But Kepler did not know this, and he did not plot like this. Okay, today this is what Google will tell you. But Kepler did not have those services. Not even ChatGPT to ask what is the relationship between these two. But he himself was much more than ChatGPT. That's another story. So even here you see that it's linear. 5,000 to 10,000, 10,000 to 15,000, the distances are same. But if you have the same linear scale here and a linear scale there, then you have to plot these two as t square and a cube. Now, what in the dream can you have to say that I should square one and cube the other? Impossible. You have to be really insane to come up with this. It's not like he tried, let me try t versus a, no straight line. T versus a square, no straight line. T versus a cube, no straight line. Then let me try t square versus a, no straight line. Finally, he got t square versus a cube as a straight line. He didn't do this. That's no way to do science. he used logarithms, which I have not put here. If you plot the logarithm of time versus logarithm of this the distance, automatically you get a straight line. And if you take the slope of this line, that will come out to be 3 by 2. The slope of the line comes to be 3 by 2, from which you will find out that this has to be cube and this has to be 2. So the powers come from that. The powerful nature of this logarithmic plot is that you can discover the power to which one parameter has to be raised with respect to the other. This was not available to Kepler. He had to invent everything by himself and then use that for his particular problem, and he came up with this. Okay? So this is the third law, called the law of periods. So we are done with 3 laws of period, Kepler. Okay? But the motivations for Kepler were not exactly the astronomy problem itself, but it was something else. But it worked very well for astronomy. Okay? So this I mentioned to you that it's the first instance perhaps of big data analysis to find a pattern. So this is an area of high importance in scientific research today. Okay, the times are gone when one person sits in the lab peering through a microscope or a telescope, takes data and then solves. So now it's a time when you collaborate with tens and hundreds of scientists from all over the world, and then you collect the data which will take several years. If you take some of the satellite data for about 2 days or 3 days, the collective efforts of all the scientists would take several years to understand what the data is trying to tell us, in spite of powerful computational facilities we have. Okay? So from here I make a slightly quicker step. In the next 10 minutes I would like to finish. Is that okay with you? Another 10 minutes? Okay, thank you very much. Online people always have the option of switching off. You people don't have. Okay, so the first impact, now I'm going to talk about the impact that the 3 laws of planetary motion had on the growth and development of astronomy. The first impact that we see is in the enunciation of Newton's law of gravitation. Newton's law of gravitation, for the interested students, I just quickly scribbled and then put that there. I didn't have time to plug in the equations. It takes a long time in PPT. So if you just take, for example, any object which is moving in a circular orbit, approximate it now, then you'll find that the centripetal force which keeps an orbit going around, for instance, the moon going around the earth, will lead you to this particular relationship that the force, centripetal force, is proportional to 1 by distance squared. Okay? And this is the law that we know as the universal law of gravitation. So the way Newton gave, it was only this much, law of gravitation. Force of attraction is proportional to 1 by distance squared. So as you increase the distance, the force of attraction diminishes. Okay, you double the distance, the force of attraction diminishes by a factor of 4. It will become 1/4. If it is tripled, it becomes 1 by 9, and so on. So Newton actually used Kepler's laws of planetary motion to arrive at that. That you will actually see in this particular step, where this t square that you have in the denominator is replaced by some constant of proportionality k times r cubed. R cube is the same as a cubed in my previous slide. So that gives you the inverse square law. So that's the first impact. And we know how law of gravitation completely changed our understanding of the solar system and many things that happen on the earth. It became the first law to explain not only falling bodies on the earth, but also the motion of planets around the sun. So there was one law which could explain both terrestrial phenomena as well as celestial phenomena. So truly it became a universal law of gravitation. After all, I told you that by universe we mean solar system. Okay? So that was the first one. So A more useful way of writing Kepler's third law is like this. This is a period squared, and this is some constant of proportionality that we talked about. This whole thing is k, and this is r cube, the distance cube. Okay, that's how you do that. And later we will see how important this particular form is. The next thing which is related to the great impact of Kepler's laws of planetary motion is in the formulation of general theory of relativity. Not directly, but slightly indirectly. Kepler's laws gave, so to say, an observational evidence for general theory of relativity. We'll not go into what this general theory of relativity is. We'll look at what the problem was. When you look at the motion of planet Mercury, the first law of Kepler says, first law as we know today, that it should be elliptical. So by elliptical we mean that the orbit has to be closed. Wherever it starts, after one revolution it should come to the same starting point. But actually people observe that it doesn't quite come to the same starting point. So it will be slightly shifted. So over a large number of years, long years, you'll find that the orbit of Mercury itself will be shifting. They have shown in this direction, it doesn't matter. In space it is equivalent. So you just go like this, and we didn't have an answer to this because Kepler's law says that it should be elliptical, but the ellipse is not being completed by Mercury. Then what could be the problem? This had been observed, but we didn't know. And that was one of the inspirational problems for Einstein to come up with general theory of relativity. So he brought in the concept of space-time with which he could explain why the elliptical orbit is not closed on Mercury. But is Mercury something special? Actually it is not. All planets and every object which goes around another object will never complete its elliptical orbit as we know now. Okay, so the ellipse itself is a bit of an approximation. So is Kepler's law then? Yes, yes, yes. But it was more in the case of Mercury, and since Mercury takes only 88 days to complete one revolution, in 1 year how many revolutions have you studied? Something like 4 revolutions. And if you have done it for 100 years, you have data for 400 revolutions of Mercury. In 400 revolutions, you can actually see quite a substantial shift in its orbit compared to Earth, where you have to wait for 400, not 400 years, but lot more. Because the shift is small, therefore you need longer period of observation. Okay, so it's very fortunate that people like Einstein took note of this. So is Kepler's law wrong then? Kepler's law is not wrong, but it is less precise. So in the case where the gravitational field is not very strong, objects will complete their ellipse. Where it is very strong, they don't. Even in the weak one they don't, but it takes a very long time for you to even realize that, even with very precise measurements. Okay? Yeah? It doesn't give a launch, but then it doesn't complete the orbit. It looks like it's going in a spiral path. And the next one, where it has made a deep impact, which fetched Nobel Prize to these 3 people in 2020. So we are talking about something very recent. So we would like to leave out Sir Roger Penrose from this discussion. Though all 3 were given Nobel Prize for their work on black holes, the contribution of Sir Roger Penrose was for his theoretical contribution to black holes. And for these 2 people, Andrea Ghez and Genzel, they were given Nobel Prize for discovering something called supermassive black holes. And then these 2 gentlemen on the left hand side that you see, black and white, Russell Hulse and Joseph Taylor, they got a Nobel Prize in 1993 for a very interesting discovery. And in both cases, It was a slight deviation from Kepler's laws of planetary motion which was responsible for people to see that something very unusual is happening there. Because if everything is normal, everything is happening as it should happen, then Kepler's laws of planetary motion should be valid at all times, everywhere in the universe. But if it is not, then something special is happening there. Now you can say, like Kepler did with Tycho, two options he had: say that the measurement is wrong, theory is correct. So even here, you can say that Kepler's law is wrong, but something new is happening there. Or you can say that nothing new is happening there, Kepler's law is all right, but our measurements are not precise. And in astronomy, it's not very easy to see which of the two possibilities is correct. If you do an experiment in a lab like this, you have a question like this, whether it is because of this or that, you can do 100 experiments to rule out this and accept this, or rule out this and accept this. But in astronomy, you don't have hundreds of specimens which have the same behavior. You can't do experiments with more than one system, most often. So that's why there is a joke that astronomers generalize after observing one particular system. They say everything is like this. Okay, and so much so that the joke is that once when one of the scientists happened to see in a grassland there was one black sheep, and he said that, oh, this grassland is full of black sheep. Immediately the neighbor said, are you an astronomer? And, it's like that, you see one and then you generalize, but that was not the case. But in this case, I'd like to spend 2 minutes on this. Very important discoveries in our own lifetime. It has happened in your lifetime, my lifetime. So we should know this. What did these gentlemen do? Hulse and Taylor were actually working on two pulsars. Pulsars, these are the last stages of a massive star, and they emit radio waves which can be detected by us, but they are not visibly seen. You don't see them through an optical telescope, but you can receive the radio waves that are generated by them. And these pulsars are known to be very, very precise clocks. Okay, so this is diagrammatically showing some radiation coming out of this. If your telescope is somewhere there in the direction of that, you will, which means the Earth is in that position. Okay, so you receive the radio waves there. So this will go around. When it comes here, the Earth is actually missing the radio waves coming towards it, and then when it again comes back, you receive. If you take the time between two radio signals received, that will be very, very precise to a millisecond. To a millisecond. So there are pulsars called millisecond pulsars. So they have a number of radio pulses given to you in 1 second. If Kepler's law is true for these two, which are going around a common center of mass, so you see the two orbits there, there is an intersection. So at the center of that intersection is the center of mass. So this fellow, one pulsar is going around like this, the second one is going around like that, both of them going around a common center of mass. Now the law of periods must be true whether it is a pulsar or it is a planet, whether it's a comet or whether it is an asteroid. But Hulse and Taylor observed that there was a systematic variation in the time taken by them to complete one revolution. And how did they find out that it was taking a different amount of time to complete one revolution? The rate at which they were receiving signals, radio signals from this, it was becoming quicker and quicker and quicker. Okay, and because these pulsars take very less time to complete one revolution, even if you were to observe for about 5 years or 6 years, you would have an enormous amount of data to solve. Solve in the sense to find pattern. If you want to get good pattern, you should have more number of things. Suppose I just wrote 1, 2, predict the next number. It's very difficult. There could be so many solutions to that. But if I told you 1, 2, 3, 4, now you are in a better position to say what the next number should be. So more the data you have, easier it is to find a pattern. So people did this. It was first observed in 1974-75, and then since then it has been done, and this is the curve you get. What this curve shows you is the shift in the position of this orbit. It is shrinking, the orbit is becoming smaller and smaller in a very predictable fashion, and this blue line that you see is what Kepler's law of planetary motion would predict, depending on the fact that orbit is shrinking because some energy is being lost. If you know how much of energy is being lost per revolution, then Kepler's law of planetary motion can be used to get this blue curve. And all the red dots that you find are the actual data that has been observed. Actual data. How the rate at which the orbit is shrinking with the time, if you plot that, and then you take into account a certain amount of energy is going away, and because of that, by how much the orbit should shrink, according to Kepler's laws of planetary motion, you'll find that the theory and observation match 100%. Credit should go to the pulsars which keep their clock going without any change. If for some reason the pulsars lose their clock periodicity, then you would not have this. Or for some reason, if the Kepler's laws of planetary motion does not hold good for pulsars, even then you don't find this. Kepler was right. His principle was right. His principle was absolutely right. There is no other example that I can think of where theory and experiments or observation data match so precisely as in this case. There is no other data that I can recall. And for this discovery, what did they discover? They discovered that energy is being lost at a certain rate. They calculated it. Now, it's not enough if you simply say that energy is being lost. You should say, what is taking away that energy? And that is where C.V. Vishveshwara sir again comes into picture, his work on gravitational waves. So he showed that if you have these black holes going around, or if you perturb a black hole, they produce gravitational waves. And to produce any wave, energy has to be produced. Because waves are carriers of energy, or waves are energy themselves. So if you are creating waves, you are creating energy. So if you believe in law of conservation of energy, you know that you cannot create energy without spending energy. Okay? I mean, that's the reason why walking, running will help you to slim down. Right? The conservation of energy. So you have to spend energy to do work. So even here, that's the same thing. If you assume that all the energy is being lost because of gravitational waves, Mr. Einstein had given a formula how to calculate how much energy is lost per orbit. And if you put the two together, and if you believe that Kepler's laws of planetary motion are valid even here, then you come to a very, very grand realization that gravitational waves must be really existing. Until this point, people did not believe in gravitational waves, including Einstein. They doubted. Mathematics is predicting it, but doesn't mean that physically it should exist. So this was a kind of a circumstantial evidence. It didn't directly show that. It is a circumstantial evidence. So there is a policeman gets into my house, there is a dead body there, and I have a knife in my hand. So what do you conclude? Circumstantial evidence is that I have murdered the person. So it's like that. You had a circumstantial evidence. And later on, people actually showed that it is indeed the case. Therefore, Kepler's laws of planetary motion have an impact in verifying this general relativity for a second time. First time was Mercury's orbit, second time is this. Every time there's a deviation, something new comes out of that. And this is the work for which Andrea Ghez and Genzel got Nobel Prize. They discovered what is known as a supermassive black hole at the center of Milky Way galaxy. Now we know that at the center of every galaxy there is a strong likelihood of a supermassive black hole sitting there. How did they do that? What they did was, this itself is a specialized topic which requires a lot of discussion. I am removing all the details. What it means is that they could actually track individual stars. Each of these bright spots is a star at the center of the Milky Way. Now, if you are to look at through any kind of a telescope towards the center of Milky Way, you will not see anything sharp like this or clear like this, because the center of the Milky Way is so much covered with dust, cosmic dust, that you can't see anything. It is like a horizon. There is a center of Milky Way, and from here to this point there is a lot of dust. So if you are sitting there and observing, all you can see is from there to here. What is beyond this towards the center, there is no way of knowing at all, because the dust will make it all opaque. But it was the brilliance of Andrea Ghez and Genzel that they came up with a very special technique of processing light coming from that. It's called adaptive optics. And using that, what they did was to follow the trajectory of each of these. This blue line is the trajectory of each star. They had something like 20 stars or so which could be tracked, and these stars, which are very close to the center of the galaxy, they seem to be misbehaving as far as Kepler's law of periods was concerned. It's not going according to t square proportional to a cube, something else. Now, if you believed that this is indeed still true there, and you apply your general relativity, then they came to the right conclusion that the center of the Milky Way must be having an extremely compact object of enormous mass. By using Kepler's laws of planetary motion and Newton's law of gravitation, they could even determine the mass of this central object, the supermassive black hole. It turned out to be something like 4 million times the mass of the sun. Okay, so Kepler's laws of planetary motion once again helps us to come up with something new object which we had never ever thought would exist, the supermassive black holes. And finally, this is my last example. There are many more examples that we can go about, but this is just to give you a flavor, and I've carefully selected the examples which gives you the width and the depth of planetary motion laws that have affected astronomy. So this is a galaxy, same photograph of these two. This is an animation actually. I have taken one particular frame from the video. The pink one is actually some kind of matter which you don't see through an optical telescope or other telescopes involving electromagnetic radiation. You use X-rays, you use radio waves, you use infrared waves. None of them will show you any matter, much matter here, but this is one. This is a simulation, as I told you, computer simulation. When you run this simulation, actually what you see is that this part goes, the pink one goes faster and faster and faster compared to the other ones, like this part, which goes as it should according to Kepler's laws of planetary motion. So again, it looks like this part is violating Kepler's laws of planetary motion, or you could say Kepler's laws of planetary motion is not valid here. Which of the two is right? It's not a defined matter actually. This is what is known as a dark matter. So the way people came to something like a new form of matter that is not familiar to us, the dark matter, is by observing the deviation from the Kepler's laws of planetary motion in the rotation of a galaxy. Otherwise, it's very difficult for you to detect dark matter, because dark matter does not emit any form of electromagnetic radiations which we can pick up from our space telescopes or ground-based telescopes. No way of finding out. So it has made it possible. And that is going to actually have a big impact on cosmology. Big impact on cosmology. So that brings us to the question, whether all the matter that we know in the universe is the matter that we are all made up of, or is there a new form of matter? Now we know that there is a new form of matter. And what is very disconcerting and which makes us uncomfortable is that nearly 90% of the matter in the universe is supposed to be made up of this pink colored one, the dark matter, and what we think is the universe is only 10% of the matter that we are able to investigate. Which means all the model of the universe that we know is by investigating 10% of matter. We don't know what kind of a new universe will come out when we understand what this 90% of matter is about. Okay, but this has been again facilitated by the Kepler's laws of planetary motion. But like this, there are a number of other examples. I can leave it to you to look up on the internet and try to look for yourself. The twofold reason why I took this is that planetary motion, though it's 400 years old, it is still alive and kicking, and every time we see a deviation from that, something new comes out of it. And that's how science grows. If nothing changed, there'd be no new things coming up. So you have to see these deviations. Okay, so I think with that, I should be stopping. Oh, one really last one, 30 seconds I will take, sorry. Now we come to the other Kepler, the discovery of exoplanets. Now we have planets going around other stars outside the solar system, exoplanets. So these exoplanets have been discovered again using Kepler's laws of planetary motion, directly and indirectly. Okay, there are many methods of detecting exoplanets, but one of the common ones that people started with is using Kepler's laws of planetary motion, believe that it applies to planets going around other stars also, and then they come up with these stars, exoplanets. Once you know that exoplanets are possible, finding that something is possible is the biggest step. Once you know something is possible, then you'll find ways to detect that. So now we have something called a Kepler satellite mission. It's been rightfully called Kepler satellite mission. That's why I put Kepler, the other Kepler. So it's the Kepler satellite mission. It's a robotic mission, and it has so far observed something like 2,778 confirmed planets going around other stars as of June 16, 2023. This I picked up from Wikipedia. Okay, it is from a peer-reviewed paper. So not just Wikipedia, it's from a paper. So in the last 6 months, it would have only gone up by some more. Okay, so it took a long time for us to find the first exoplanet, but once the first one had been done, to go from 0 to 1 is the biggest block. To go from 1 to 3,000, it doesn't take much time. This has happened in a matter of just 9 years. And we have taken 5,000 years to find the first exoplanet, but only 9 years to find the remaining 3,000 planets. That's how technology and science go together, thanks to Kepler's laws of planetary motion. Okay, so I think I'll stop here. If you have any questions and time, I will be very happy to take some questions. Yes.
Just a second.
I can hear him. Sorry, please come in.
Talking about Kepler going through all of Tycho Brahe's collected data, the main problem I thought of was the entire collected data was in the terms of geocentric model. So the Mars and everything, all the positions were behind a backdrop of stars, and that was a fixed position which was taken. So there is a rotationary, revolutionary period which was determined based on the fixed data from that.
Yes.
But as soon as Kepler realized that we has to use a heliocentric model, the revolution has to be figured out as to when the year completes once more. So he has to figure out how the data is skewed and again correct for all of it to figure out the actual values then.
Yes, yes. So he should be very familiar with the method by which Tycho Brahe collected all the data, but that was not enough. He had to believe that the Earth goes around the sun, because all the orbital periods that you have is for going around the sun that Copernicus gave. And Copernicus was very careful for various reasons. He said this is only a model. But Kepler believed it to be real. So there is a big shift in saying that this is merely a model, a hypothesis, or this is what I think, to saying that no, this is exactly how it is. Kepler had that big shift. Very often these revolutionary ideas come first in the mind, then the revolutions happen outside. The first revolution is in the mind. Now Kepler must have been thinking, should I go for heliocentric or geocentric? That's not easy. Your observation is absolutely right. So for every data that Tycho had done, he had to convert that in terms of a heliocentric coordinate and work for that. So that also explains why he took such a long time. Can you think of anybody being obsessed with one problem for 17 long years? We don't. See, Tycho. How did he do it? Tycho was a nobleman. He came from a very rich family. So for him, it was not a problem, sustenance. And much of that wealth was also used for sponsoring Kepler's work by Tycho Brahe's son. So Kepler did not have to think much about the payment part. Is it the question you asked? Yes. No, it's a very important question. Yes. Yeah. If you allow me, in that context, I would like to show one slide which I skipped, just to tell you, just to show you how we all complain about lack of facilities and we don't have this, we don't have that. But for that facility, I would have been first in IIT JEE. You should read this. These are the problems of Kepler. At the age of 12, I nearly died of smallpox. My hands were badly crippled. During the age 14-15, I suffered continually from skin ailments, severe sores, scabs, putrid wounds on my feet, which would not heal. On the middle finger of my right hand, I had a worm, a huge sore on the left hand. When 16, I nearly died of a fever. So many times he almost died. When 19, I suffered terribly from headaches and disturbances of my limbs. I continually suffered from the mange, which is a kind of a skin disease, kajji antivala, and the dry disease. At the age of 20, I suffered from a disturbance of body and mind, as though before that it was not enough. This is the kind of health status of Kepler for a good part of his life later on also. He didn't have a good health, but that never came in the way of his work. Okay? And of course, his other things about his family were not great. We should not sensationalize Kepler through showing down the family, not necessary. But what stands out is that in spite of all these things, Kepler was fully focused on the problem that was there, and for 17 long years. That's an inspiration we can all draw from him, his style of working. So socioeconomic, you said, I thought I'll just mention this. That's right. It's very important. Yes, Tycho did that. Though he reluctantly did that to Kepler, To start with, he did not part with all the data, but then he knew that if there is one person who could solve this problem of Mars's orbit, it was only Kepler.
It was a circle, and then it was an ellipse, which also had some symmetricity. But then you said it is not even a ellipse. I mean, it doesn't traverse the same path all over again. So we were back to non-symmetricity again,
Ah.
in a way. So, now just reminiscing whether what is this symmetricity about? Where is that coming from?
No, that symmetric argument came mainly from their religious beliefs that the whole system is created by God, and then God is perfect. God creates only perfect things, and by perfect they meant symmetry and even the periodicity. If you have the circular motion and it is uniform circular motion, same speed everywhere. But Kepler killed both the ideas in one shot. He showed that the orbit is not circular. He showed that the motion is not uniform. Because Earth was moving faster in January and slower in July.
Except that the area of the triangles were the same. That was the only sort of
That
constant.
was the same. Exactly. It was exactly that periodicity, sir, that you are talking about. It's exactly that periodicity that you are talking about, which drove him to the third law of Kepler, because this is a kind of a repetitive pattern you see even in music. So there is a harmony among different notes. Therefore, if there are different planets going around the sun, there must be a harmony. So he created musical notes for the motion of each and every planet, and he felt that a combination of all this would be a harmonious music. But I can tell you, after getting this composed for different planets and playing them together, it is a bit of a cacophony. There is no music in that. Doesn't matter. We can excuse Kepler for that.
Was Kepler ever death sentence? Because many people like Copernicus, when he suggested the heliocentric model, they said they'll kill him.
Uh,
So had they ever done that to Kepler?
See, Copernicus was a very pious man. He was a very pious man, a God-fearing person. So he very, very smartly, I told you for some reasons, he only told that it's a mathematical model. It's exactly for this reason. I didn't want to sensationalize things unnecessarily, but since you bring it up, I'll tell you, his religious belief did not allow this model to be accepted as a real thing. So that the religious authorities did not mind Copernicus publishing these ideas as a model, but they had a problem if he published these things as a reality, because that would go against the authorities, religious authorities, which believed otherwise. They had a different set of beliefs, and this belief was clashing with that. Okay, so Copernicus did two things. One, he was very careful in telling that this is a mathematical model, so nobody can claim that he is saying that the religious belief is wrong. And secondly, he did not publish the book until the day of his death. Okay, so it was published only on the day of his death, so there was nothing that people could do anyway with it. That I don't know, sir. That I don't know. Huh? I have not gone into the details of that, but whether coincidence or not, it was published on the day of death, so he was spared of any kind of punishment or threat that religious authorities would have given to him, like they did with Galileo later on. Okay, so that did not happen, and Kepler also did not face any such things, but Galileo did.
Can you play that sound?
You play that sound. I hope it works. I'll come out of this PowerPoint and I'll go to the folder. Then there is Mars. Mars. Sorry? Remove? Okay. I am able to hear. There is saying they are not able to pick up on this microphone. Can somebody help me? Either speaker will everything. It's very basic, goes faster. And these are exactly the notes given by him. Okay, and this is Mars. There is, as you go farther and farther, it becomes more and more. Okay, so he felt that there is a harmony, and he was driven by that to find the harmony among the planets.
Atul Bhatt has a question.
Oh goodness.
It was asked long back. Were there any laws before Kepler's, or were Kepler's law the first in physics, or at least respectively the first chronological law in physics that we still study and hasn't been proven wrong?
You see, definitely in astronomy, this is the first mathematical formulation of any behavior that we know. But then as a law of physics, I am not too sure. There must have been, no, even Bernoulli's came much later. So I can almost put my head on the guillotine and say that this is the first law of physics that we would have. I'm putting my head on the chopping block. I'm almost certain. Almost certain. Atul, I have to answer him. Atul, I hope it answers your question.
And then there is one more question from Ms. Purnima Hosur. So she has asked, what if Earth's axis is perpendicular to the plane of its orbit?
What if
Earth's axis is perpendicular to the plane of its orbit?
many things that could happen, so depending on what particular aspect you would like to see. So if you see in terms of seasonal variations, if it were to be perpendicular, then you would have specific places on the earth with specific temperature distribution all through the year. You would not have the variation in seasons that you have now. because of the tilt of 23.5 degrees. So that would be one impact. Remember, I mentioned to you that it's very important to ask what if questions in science. So this is one such what if question. If you say, what if the Earth's tilt were to be perpendicular instead of being 23.5 degrees? Now you try to see what are the various things that we see because of 23.5 degrees, and then you ask for 90 degrees, what would be the impact? So one immediate thing would be about the seasons.
Madan Reddy has asked a question. Sir, what exactly is meant by harmony of worlds?
Harmony of worlds is the phrase that Kepler gave. He wanted to see a nice relationship that exists between periodicity of a planet around the sun and its distance from the sun. Okay, so the fact that the power of t and power of distance r, they are integers like t squared and a cube, and in those days people believed that God created integers and men created fractions and decimals. Okay, fractions and decimals are always metaphorically seen as something imperfect. Integers are always seen as something whole and perfect. And since God created the universe as they believed, so the integral relationship between t and a showed the harmony between these different parts of the whole universe, and that's why he called it the harmony of worlds. He was also a God-fearing person, Kepler. Yes, very much. But very interestingly, he kept God out of his science. He could distinguish between them. He did not mix his scientific work with his understanding of God and things like that. So God was more of a spiritual necessity for him, which it is like for most of us. Spiritually, you can believe in any of these things. If it brings happiness to your mind, why not? But then if you say that I'm doing science, then you say, is it supported by an experiment? If you do that, then it is excellent. So Kepler was very careful about keeping these two apart. Any other questions? Yeah, no more questions. Once again, let us thank you all. Okay, thank you very much. Personally, on behalf of the institution, she will do for.
Oh. So first of all, thank you all people for coming here on a Sunday evening and spending time with us. So I'm sure that you people all have enjoyed the talk. So let's thank Matsudan sir for the wonderful talk he gave. Yeah, keep coming back to Planetarium for all our programs. Thank you. Thank you, one and all. Between 17th and 19th of January, we have a program called Universe in the Classroom. It will be in the evenings, 4 to 7. So it will be on some basic concepts in astronomy. So if you people are interested, it will be open for people who are about 13 years. So it's not like any restriction over there. So anybody above 13 years who is interested in astronomy can register for that program. Thank you.